that we've been discussing. So if I think about that first function for number 5, we have f of x is x squared plus 5x minus 14 on top, and x squared minus x minus 2 in the denominator. Automatically, I see that it's degree 2 over degree 2. So we do have a horizontal asymptote. Degree 2 over degree 2 means it's the same on top and bottom. We're going to use our leading coefficients. So on top we have 1x squared. On bottom we have 1x squared. So it's 1 over 1. Our horizontal asymptote is just y equals 1. I'm going to go ahead and put that on my graph. So I'll use this red pen for the horizontal asymptote here at y equals 1. And then if I factor this, we have f of x as x plus 7, x minus 2, over x minus 2, x plus 1. So there's a common factor that creates a whole. That whole is happening when x is 2. And if I plug 2 into the x's of our reduced function, we get 9 over 3, which is just 3. So we have a whole that's sitting here at 2, 3. In this graph, you just want to make an open circle at that point 2, 3. The vertical asymptote is coming from the denominator, and we see that x plus 1 is the only factor left in the denominator, so the vertical asymptote is at negative 1. We can find some more points like the x-intercepts and y-intercepts. X-intercepts, when I look at the reduced function, it's x plus 7 over x plus 1. And setting that equal to 0, I would multiply the x plus 1 over here and still get 0. 0 times anything is 0, which means I have an x-intercept at negative 7. And then we'll look at our y-intercept. The y-intercept is the value of y when x is 0, which just makes this 7 over 1, so I have a y-intercept at 0, 7. I'm going to plot both of those points. This is still not a lot of information, but it does give me a good idea of what's going on around this graph. If I was going to graph this, I know I'm going to need to come from that asymptote at negative 1, the vertical asymptote, and go through the y-intercept, go towards the hole, and we are going to approach this horizontal asymptote at y equals 1. We have another little bit of an idea what's going over here on the left. On Alex and some of the other assignments, you will need to have more than one point, so I'm going to make a table, and I'll just do this off to the side because I'm kind of running out of room. But we can use our calculator to help us with this. So maybe I'm curious what happens around negative 2, negative 3, negative 4, some of those. I can plug this into the reduced fraction, or I could go back into the original, either one. But let's say I do negative 2 plus 7 over negative 2 plus 1. We get negative 5. So I know automatically there's a point at negative 2, negative 5. We can do it again with negative 3. So negative 3 plus 7 over negative 3 plus 1 gives us a point at negative 2. So negative 3, negative 2. I could do negative 4 Negative 4 plus 7, negative 4 plus 1 gives me negative 1. We don't always get nice points, but that's enough information for the left side of the graph. We can see what the general trend is. We're going to approach the asymptotes as well. We have a graph that's something like this. Now 6 is a little bit more complicated because we'll notice that we have 3 factors on top, which makes this degree 3. And we have 2 factors in the denominator, so degree 2. Looking at the factors, I see that none of them are common, so this does not have a whole. But we do see some vertical asymptotes. We might find some x-intercepts, and we're going to have a slant asymptote. The issue with finding the slant asymptote is that I need this in standard form to be able to do the long division, which unfortunately means I'm going to have to multiply some things out. So I'm going to do this on a separate sheet of paper for a second. If I multiplied out 2x minus 7 times x plus 5 times x minus 1, just the numerator. Let's start with the x plus 5 times x minus 1. This would distribute and I would end up with x squared plus 4x minus 5. And we're multiplying it by 2x minus 7. So then I distribute again. I get 2x cubed. And we continue on, 8x squared minus 10x minus 7x squared minus 28x plus 35. So to finish all that out, that's 2x cubed plus x squared minus the 38x plus 35. That is just the numerator. And now we would need to know what the denominator is. All right, our denominator was x minus 4, x plus 3. So that would multiply out to be x squared minus x minus 12. All right, so that would be our function in standard form, I guess. 2x cubed plus x squared minus 38x plus 35 over x squared minus x minus 12. We still need to do the long division for that. All right, so I'm going to do that back here on this original paper. This would mean I'm doing x squared minus x minus 12, and we're dividing that into 2x cubed plus x squared minus 38x plus 35. All right, so 2x cubed divided by x squared would be 2x. We multiply that back through. And we subtract. All right, so we have a 1 minus a negative, that's plus, that's 3x squared minus 14x plus 35. I divide again, so x squared goes into 3x squared 3 times, so plus 3. And we subtract that whole row. I get negative 14 minus plus, so negative 14 plus 3 is negative 11x. 35 minus a negative 36 becomes plus, that's 71. But that part doesn't really matter because this is our remainder, and we ignore the remainder when we're finding a slant asymptote. The only part that is going to be important is the quotient, 2x plus 3. So we have a slant asymptote at y equals 2x plus 3. This is the first one that we've gotten like this, so I'm going to go ahead and help us graph this. This is a linear function where the slope is 2, and the y-intercept is 3. So I'm going to put my y-intercept first at 3, and the slope is positive 2, which means I'm going to rise 2, run 1. It's rise over run. We can go down to left 1 to find more points. The more points you plot, the easier your graph is going to be, or more accurate at least. But this is a asymptote, so I'm going to do like a little dashed or dotted line here. I did skip the vertical asymptotes. We know that there's no horizontal asymptote since there was a slanted one, but the vertical asymptotes come from that denominator. There weren't any holes, but we have 2 vertical asymptotes. So one's at positive 4 and another one is at negative 3. So negative 3, let's draw that one in here. And then again at positive 4. All right. If we find the x-intercepts, we actually have a few. So let me do that over here, x-intercepts. This is when the function is equal to 0. Hopefully we start to see some patterns emerge about where do these different characteristics come from in the function, and do we want it in standard form, do we want it in factored form to help find those different things. If I multiplied our denominator over to the other side, it would still multiply to be at 0, which creates this polynomial equation that we're dealing with, but we solved these previously. And so I would have a solution at 7/2, another at -5, and another at positive 1. And these are all the x-intercepts. So 7/2 is 3.5, so that would make 3.50. Another one at -5, and another at positive 1, 0. So I'm going to just go ahead and graph what I can. 3.5 right there. -5, we'll put that here. And I can find the y-intercept. This one, I actually prefer using our standard form equation for your y-intercept because that makes it a little bit easier. But this would make this 2 times 0 cubed plus 0 squared minus 38 times 0 plus 35 over, we've got a 0 squared minus 0 minus 12, which just makes 35 over 12. That's almost 3, so we'll use our calculator, but 35 divided by 12 is 2.9-ish, so we can say approximately 2.9. And we can see that we're actually really close to, actually, that would be a -12, so a -2.9. We'll change that point down here. Apologies, ignore this one. All right, I don't have a lot of points, and that's one issue with these, but we can kind of see what's happening. This is not a perfect graph, but we're going to be approaching the asymptotes. And I only had 3 points here in the middle, but I have only 1 here to the left. So maybe we make a table again of some values that we can plug in. I've already got -5. Let's go to -4. And it might be easier to do this one in factored form, maybe. So we'll try it 2 times x, so -4 minus 7. And then we've got -4 plus 5 and -4 minus 1. The denominator, if I plug it in, I've got -4 minus 4 and -4 plus 3 gives me a fraction of about 9.375. That's okay. We are not looking for exact points all the time. Maybe I want to find something around -6. What's happening there? We can do the exact same thing. All right, this time maybe I'll try that standard form equation. So 2 times x cubed, x is -6, plus x squared, so -6 squared, minus 38 times -6 plus 35. Over, so we've got our denominator, -6 squared minus -6 minus 12. Gives me roughly -4.4. So 1, 2, 3, 4, roughly around there. What we're going to see is we're approaching that vertical asymptote at -3, and then we're going to start approaching this slanted asymptote towards the left. All right, we've got this section over here to the right. One thing that I will use just for logic-wise, we don't have any other x-intercepts, so there's no way that we're actually over in this section here, but there is a part of the graph that we're kind of off the grid for, so that slanted asymptote would still keep going up. This vertical asymptote would still keep going up. So there is a section over here that we just are missing, and it goes something like that. We could find, I would make more points by doing another table and just seeing what happens when x is 5, maybe 6 and 7, and that would give us the other points to plot.